Okay, let's start this part regarding the electromechanical systems. Uh, the first simple model is the fixed field system. We have this rotor part that is trying to give us the output displacement or rotation theta m, with the torque coming out as Tm. And what we have here is that the magnetic field is developed here. It's like we have some uh, magnetic field here, B, we are showing it, with some L as the characteristic length multiplied by IA as T. So it's giving us the magnetic forces or moments or torques that causing the rotor uh, uh, to rotate. So what do we have here about the fixed field? The thing is, the field here is fixed, so the I here is fixed, and we have the armature uh, part, which is, we can write the equation here like EA is equal to some resistor, some resistance of the circuit, plus like inductance of the circuit IA, plus VB, which is the voltage here, is called back EMF. So the first thing we can see is about this circuit, the voltage relationship that we can write. Next, let's see what we can say about this system. Another, so let me write this equation here. EA is equal to RAIA plus LAS IA plus VB. Now, the thing is, we have to have some assumption about the back EMF. The electromotive force or back EMF, which is the VB, we say that according to some experiments and according to some simplifications, this voltage is proportional to the rotation speed, omega m, that is the omega of the motor. So if I show this by time differentiation of the displacement with respect to time, so I can say that this relationship holds until we have the KB. And KB is some experimental constant that can be measured. We will discuss how. So the second relationship is here. VB is also KBS theta M. So I have these two equations for now. Clear until here? That how we wrote these two equations? What else I can write? I can say that another assumption is that the torque in the motor is related to some constant multiplied by the current in the ammeter and the current in the field. So if we consider this IF, then we say that IF is constant with respect to time because it's a fixed field. So here, IF as function of time is like IF. It's a constant field. So we write this as Km I AF time. So in the frequency domain, I can say T is Km IA. Another relation comes from the mechanics. That is, the Tm as the torque is being like used by some load. So T of load. And this load here, we are showing it as JMS2 plus DMS theta M. Okay. So if I insert these information into the main equation, like EA is equal to RA plus LAS IA plus KBS theta M, then I say that EA is RA plus LAS. Instead of IA, I can put TM over KM. And instead of like KB, this part can still hold. So KBS theta M. So the transfer function of the system as theta M over EA would be Km over RA plus LAS. And instead of Tm, I wrote JS2 plus DS plus KB KMS. So we have EA here, we have KM here, and this TM guy is like some relationship, JS2 plus DS theta M. So we have all here, we just rearrange them such that we can write the transfer function theta M over EA. Any question here? Make sure you understand every assumption and every relationship that we wrote here and how we wrote them. Any question? No question? Okay, then we want to add something to this. We want to say that, okay, I know that JM S2 plus DS DMS theta M is equal to T of the load, or T of M. But we say that there might be some systems in the outside continuing. So what do we do is to bring everything from here to here. Well, how we do that? We multiply them by destination to source to the power of 2. So if I want to write the Tm here, I have to write it like JAS2 plus JL N1 to N2 to the power of 2 S2, that is theta on the motor, plus also dA S2 plus D of the load coming from the next systems to the power of 2S theta M. And we don't have the spring here, stiffness here. If we have to also include them. Now, the thing is, if you go back here, we have two constants. One of them is KB, another one is Km. These two constants are usually measured based on torque speed diagrams of the electromechanical system. Now we want to show that if we have those information, how we can obtain these constants. Okay, so this is the torque speed diagram, that is torque measured with respect to the rotation speed. If we are just doing it for LA0 here to make it simplified, if I know that E of A is RAIA plus back EMF voltage with LA0. So, and I know that EA is equal to RAIA plus KBS theta M. All right. And also I know that EA is RA. So instead of, I know that TM is equal to like KMIA. So I can write this here, TM over Km plus Kb. And instead of S theta, I can write omega M, because S is the differentiation in the frequency domain. So I can say that EA is equal to RA over Km Tm plus Kb omega M. Now, if you look at this equation, if omega is 0, this is called EA equal to RATM over Km, which is T is the stall condition. So when omega is 0, let me put it here. When omega is 0, what I read from these guys, I am reading for any E, the T stall. I have the, and I can calculate based on that this constant. RA over Km is equal to T stall, is equal to EA over T stall. And if I have experiments for condition that torque is 0, torque 0 means that no load is on the motor and it's rotating freely with considering 0 friction. So in this case, I have EA equal to KB omega. What will be the omega? That's omega of the no load condition. And from here, I can find KB. So let me show an example now for the general fixed field case. Okay, so assume this is our example. It says that given the system and torque speed curve below, find the transfer function theta L to the EA. Okay, so first of all, I have to say that I will make it here very simple. Like I have the EA from the armchair is equal to RA IA, okay, plus VB. I don't have the inductor here. And EA would be RA, this guy will be TM over I over KM plus KB S theta M. Okay. Now the torque on the M, I have to write the torque on the M. Let me write the torque on the M. The torque on the motor is like 5 S2. We have this J of the armature, 5 S2, okay, plus 700 destination over 1000 to the power of 2 S2 theta in the M, okay, plus damping part, 2s plus 800 s theta M. Okay. Now I consider this guy as J equal S2 and this guy as D equal S. Now I can write that I know theta M over EA is Km over RA multiplied by JES2 plus DES plus KB KMS. Okay? And this can be written as 1 over RA over Km JES2 plus DES plus KBS. So in this relationship, what I don't know is this guy. It's not given. And also I don't know the KB. It's not given. Okay? So what do? We say that our EA is equal to RA over Km JE in the time domain. Okay? Let's make this in the time domain. JE S, let's make it in the frequency domain, and then if you need S2 plus DES plus KB omega M. This was this relationship is rewritten like this. Now, if the torque is 0, this guy is the torque is 0, I know that EA is KB omega M. So KB would be 100 volts. This is the EA over omega M, that is 500 radiant over seconds. Next, I can say when omega is 0, I have like EA equal to RA over Km multiplied by T. This guy is the Tm. That is 500. And this is 100. So RA over Km is 100 over 500. So these two guys are found. These are found here. This here. So let me make it completely simple. We have these basic relationships. We come to this guy here, okay? Then from mechanics, we also get these guys. Then we see that at final step, we don't have this KB and RA over Km. So these two guys come from this, let's say, experimental observation that when the voltage is 100 in the input, we have this 550 as no load torque and no load torque of a stall, sorry, and no load rotation. Clear? Clear, guys?
Yes, sir.
Okay, that's good. The second kind of electromechanical system is variable field. In this case, the voltage input is going to the field of electromagnetism. That is the the relationship that we have for the basic uh, input relationship is that Vf is equal to some field R, I of the field, plus LF SI of the field. So in the previous case, we considered EA as input. Here, VF is input, okay? The thing is, we want to find theta related to VF. In this case also, if we say that the torque is something like K, IAT, IFT, like the previous case, this time this guy is constant. So this relationship can be written as KMI FT. So in the frequency domain, I can write TM is like KM IF. Okay. And T of M in this case is also T of load. For this case, we want to also include some disturbance load. And I know from the mechanics that TL load is equal to J equivalent S2 plus D equivalent S theta in the S field. Okay. With these relationships, we can find the transfer function like VF is RF plus LFS IF, and IF is TM over KM. So this TM over KM, and we have this guy, so VF is equal to RF plus LFS JS2 plus DES theta S over TM. So from here over KM. From here I can find the relationship between these theta and V. This one is much more simpler than the previous one. So you can see in one page we came to the transfer function as here. Now we want to say that, okay, these transfer function, can we show it as block diagrams that we had in the first week. We said we have some functional block diagrams and we want the relationship inside them. Let's see if we can do it. In this case, I know that I have to start the relationship with VF equal to RF plus LF S multiplied by IF. And I know that TM, this part is KM IF, okay? And I know that TM, like plus minus some T disturbance, let's say, is equal to TL if I want to include this guy here. Okay, I want to pay attention. I want to have the input VF and output theta in the system. Here it says it's theta. So, okay. If I start one by one, when VF comes to the system, what do I have here? If it's multiplied by 1 over RF plus LFS, it gives me, it's like VF multiplied by 1 over R plus LS, gives me what? IF. So the signal I get here is IF. Then I can say that this IF guy multiplied by Km gives me the torque M. So, sorry. Multiplied by some constant Km gain gives me Tm. Then Tm is like disturbed by some disturbance gives me T load. Then I know that this T load guy is JES plus D omega. So this T is multi over JES plus D gives me omega. And this omega guy, when integrated by 1 over S, gives me theta. So the system is the system we represented here is an open loop control system, and we can show it by multiple block diagrams. Clear? Clear, guys?
Yes, sir.
That's good. Okay. Now let's do the block diagram thing for the fixed field. In the fixed field, the equation was like EA equal to RA plus LAS IA plus VB. So if I start with that, I can say EA guy comes here. Then I need minus VB to get EA minus VB. And multiply it by 1 over RA plus LAS, and I get IA. This is the blue relationship. Yeah? It's like EA minus VB is equal to RA plus LAS multiplied by IA. The green equation, we know that then IA is like Tm equal to Km IA. So this guy multiplied by Km gives me Tm. Then I can also say that Tm guy plus minus T disturbance is the load. So plus minus disturbance is TL. And I know that this TL guy is J equal S2 plus D equal S theta, which means that I can write it like 1 over JES plus DE gives me omega. And then in order to show the exactly what is going on, then I have theta. We separate omega and theta. So how do I get this VB? The VB relationship here, we don't have two inputs. The VB relationship is like this. I know that VB is KB S theta, or it's like KB omega. So if I get something from omega, bring it here, and I have this KB, because this guy is omega, this guy is omega KB, so this is equal to VB, and negative feedback gives me the system. So we have a closed loop negative feedback system that gives us the representation of the electromechanical system with fixed field. Clear? Okay.
Yes.
Okay, that's good. If you have any questions so far, we can discuss.